Today in class we were talking about drawing Lewis structures, which essentially are going to represent what a molecular covalent compound looks like. We will only be drawing these structures for covalent compounds, which we know are two or more non-metals bonded together. What you'll notice is that when we draw the covalent compounds, we represent the shared electrons, because we know covalent compounds share electrons, with a line representing the shared electrons. So you'll see the line here and here. You'll see above or around some of the atoms there are little dots. Those represent what are called lone pairs of electrons. These electrons are owned by the atom that they are next to, where again the line represents shared electrons. Electrons in this case are shared between carbon and between chlorine. One of the rules that we need to follow is that all atoms, when they share electrons, must have 8 electrons surrounding them. So you'll notice with fluorine, over here there's 2, 4, 6, and the 2 shared electrons make 8. Every single atom, with a couple of exceptions, must have 8 electrons surrounding it. This is called the octet rule. So this is page 34 in your packet. So let's go ahead and take a look at the next page. So what you'll notice is that we need to figure out which atom is going to be the central atom in each of these structures, because they start with a central atom and the other atoms are bonded around them. So if you look at sulfur, SF3, sulfur is a central atom. It's really easy to tell which the central atom is going to be because there's typically only one of those. So it would be the atom with no subscript. Sometimes it's also listed first. This does not always happen, so you have to be careful with that trend. So the central atom in CO2 would be carbon, in PH3 would be phosphorus, and SiO2 would be silicon. For each of the compounds that we looked at in question 9, we need to figure out how many total valence electrons each of those compounds has. And in the past we've done valence electrons for just singular atoms and elements, but now we're going to calculate them for an entire molecule. So you see that with CO2, what they did was they said, okay, we've got one carbon atom, so this represents the number of atoms of each element, and this number represents the valence electrons. And then you're going to add up the totals. So with CO2, there's one atom of carbon with 4 valence electrons, and there are 2 atoms of oxygen with 6 valence electrons. 4 plus 12 is 16. If we do PH3, there is 1 atom of phosphorus. Each phosphorus atom gets 5 valence electrons, and we're going to add, there are 3 of the hydrogens with 1 valence electron for a total of 8. Now, it's pretty easy for neutral compounds, but when we get into ions, we have to be a little bit more careful. So it says the number of electrons that should appear in the bonding picture for CO2 is 22, or sorry, CO3 is 22. But if we have CO3 minus 2, there are 24 valence electrons. So the reason that CO3 minus 2 has 24 electrons instead of 22 is because CO3 2 minus has an extra 2 electrons due to its overall charge. And then it's just the opposite. If you look at a positive ion, NH4 would have 9 valence electrons, but NH4 plus will only have 8. Because it has an overall positive charge, it's going to have 1 fewer electrons than the neutral compound. So really important here is number 13. So make sure you get this filled out correctly. So For each negative charge on a polyatomic ion, we are going to add an electron, and for each positive charge, we must subtract an electron. It's kind of counterintuitive because you have a negative charge, you have to add electrons, and if you have a positive charge, you have to subtract electrons. That's because a negative charge means you have more electrons, which are negative. So you're increasing the negativity, which again is a little bit counterintuitive. It's a little bit backwards from the way that we would normally think. So if we're going to go through an example of counting valence electrons on an ion, let's look at NO3. There is one nitrogen atom with 5 valence electrons plus 3 oxygen atoms with 6 valence electrons, and then we're going to add 1 because of this negative sign here. So 5 plus 18 plus 1, 6 plus 18 is going to be 24. And then if you do a positive one, such as H3O, also known as the hydronium ion, there are 3 hydrogens with 1 valence electron plus 1 oxygen with 6 valence electrons minus 1 electron. 2 and 6 would be 8. So we're going to flip to the next page and take a look at some of the steps. Down in one of the next questions, they have us do an example problem with SO2. So we're going to go through those examples as we talk about the steps. I encourage you as you go through your homework to refer back to these steps as a helpful guide to creating the Lewis structures. So step 1, add up the number of valence electrons that should be included. You must do this step every time and you must show your work. So for CO3, they did that. They have 4 valence electrons from carbon, 3 valence electrons from, 3 oxygens with 6 valence electrons, and then they have to add 2 because of the charge. So they end up with 24. NH3 is 1 atom of nitrogen, 3 atoms of hydrogen, so they get 8. So we'll do sulfur dioxide, and that's going to be 1 times the 6 valence electrons that sulfur would get, plus 2 times the 6 valence electrons that oxygen would get, and we will end up with 18. Step 2, draw the skeletal structure. Sulfur is going to be our central atom because there's only one of it, and it's listed first, which kind of helps. So SO2, this is our skeletal structure. Step 3, add 6 more electron dots to each atom except the central atom. Also, never add dots to hydrogen. Hydrogen is only allowed 2 valence electrons, so it does not get a full octet. So we're going to go ahead and add 6 dots surrounding each oxygen, and we're going to leave sulfur alone. As you notice, they do the same thing on CO3, and they do not add it onto the hydrogens from ammonia because, again, the hydrogens only are allowed 2 valence electrons in their outer shell. Step 4, add any leftover electrons to the central atom. And the way that we're going to figure out the number of leftover electrons is we're going to take our total number of valence electrons and we're going to subtract the number of electrons we've already used in our structure. So we've got 2, 4, 6, 8, 10, 12, 14, 16. Even though each of these bonds represents 2 electrons shared from between oxygen and sulfur, you count each of them twice. So if you have 2 bonded pairs of electrons, you're going to have 4. So we're left over with 2. So we're going to redraw our structure just so that you can see where we left off. And we are going to add those extra 2 electrons to the central atom. Step 5, if the central atom has 8 electrons, then you are done. So let's go ahead and check to make sure our sulfur has 8 electrons surrounding it. We've got 2, 4, and 6, not 8. So we need to keep going. If not, then move 2 electrons from a different atom to make a multiple bond. You can do this up to what is called a triple bond. So when we take a look at sulfur dioxide, you'll see that, let me just redraw our structure here again so you can see where we leave off. I highly recommend doing these structures in pencil because you will be erasing electrons that you've already drawn. And it's not that we're taking electrons away from the oxygen in real life, it's just that we've drawn them on where they don't belong. So I'm going to remove electrons from this oxygen. We're going to turn it into a double bond. And we're going to double check and make sure that every atom has 8 valence electrons surrounding it except a hydrogen, which we don't have in this scenario. And we are going to check and make sure we have the correct number of valence electrons, which is 18. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So we're good there. And we've got 8 electrons surrounding oxygen, so that's good. We've got 8 electrons surrounding sulfur, that's good. And then the other oxygen also has 8. So this would be our final structure for SO2. The only difference between drawing ions and neutral compounds is that ions require a set of brackets and their charge. So NO3 is going to have 5 plus 3 times 6 plus 1. So we're going to get, we know we added this up before, 18 plus 6 is 24. So we're going to put nitrogen in the middle. We're going to put our oxygens on the outside. This is our skeletal drawing. We're going to put 6 electrons on each of our bonded atoms. And then we're going to leave our central atom alone and double check and see if we have any left over. So we have 8 on this oxygen, 8 on this oxygen, 8 on this oxygen. So we have 24 at this point. So that means we don't have any more left over to give to the central atom. So I'm going to subtract some electrons from this oxygen and say, oxygen, you have to share that with nitrogen. Now we've got 8, 8, and 8, which is 24, and everybody has a full octet. So to finish off our ion structure, we're going to add brackets and a charge. We've already done SO2 in the margin, so that's great. And your homework post doing this is going to be to take a look at pages 37 and 38. There are some tricky ones on here. I've given a couple of starters, but one of the things that you need to pay attention to is when you have two elements only, or 2 atoms only, there's not going to be a central atom. So you just bond them next to each other, and that is it. So if you have any questions, please feel free to send me an email, or we can talk about it in class. Feel free to come in early, and we will discuss any questions you may have. All right, have a great day.